Now, when we know the conductance rate, for example, and we've thought about the energetics of water, a large part of the energy budget for ecosystems, as we talked about before, goes into understanding the Bowen ratio. How much water is evapotranspired versus sensible heat produced. And that's really the main partitioning of energy that we have in ecosystems. When we measure Bowen ratios, essentially it happens in small meteorological stations like this. And there's usually a sensor, so we're going to note what the wind speed is, but there's usually a sensor, such as this one over here, that is measuring the amount of water and parcels of air going up out of the ecosystem. And it also knows from the movement of air downwards, because we have convection, what the humidity is, or vapor pressure, of parcel of air above it. And so that tells us how much water is leaving the ecosystem. And then we'll have other monitors that'll tell us the surface temperature of this ecosystem and how much sensible heat there is, how much heating of the air adjacent to the ecosystem surface. And so in a meteorological station like this, we're going to be able to determine how much water is being fluxed out of it, as well as how much heating of the air there is, and that ratio of the two again ends up being our Bowen ratio. Now the authors give a table 4.2, which is representative Bowen ratios, again the ratio of sensible to latent heat flux, and we showed this in the diagram earlier, but a desert is going to have a really high Bowen ratio because there's a lot of sensible heat that's produced, but because there's not a lot of evaporation or transpiration, very low latent heat flux, so they have 10 times more energy goes into heating the air than evapotranspiring. In contrast, something like irrigated crops or tropical wet forests have Bowen ratios that can be somewhere in the order of 0.1, where 10 times more energy goes into vaporizing water than it does to heating the air. So again, when we want to think about sensible heat flux and latent heat flux Bowen ratios, moisture availability is going to be really important to think about, because it's having a lot of moisture available then is one of the factors that are important for the amount of latent heat flux. And if you don't have a lot of moisture, you're going to have a lot more sensible heat flux. But also we need to think about the coupling of the atmosphere to the ecosystem and how efficient the transfer of energy is from the ecosystem to the atmosphere. So if there's really poor coupling, for example, and you have a surface, and let's say the air next to that surface becomes saturated. If there's poor coupling, you'll have dry air just above it. But that moisture will never make it into the dry air. You really need turbulence to start to mix the air up and take this saturated air and mix it with relatively unsaturated air. And if you don't have that coupling, you're going to have relatively little latent heat flux, because even though there might be a lot of water there, if that's available for evapotranspiration, if it doesn't become well mixed, you'll just get a relatively thin film of saturated air, and then the rest of that energy goes into sensible heat flux. So that coupling is really important for the transfers of energy and water vapor that can allow for having really low Bowen ratios, for example. And again, we talked about surface roughness as being important because that was important for coupling. And so in an uneven forest, such as this tropical rainforest, where you can tell it's not flat and you've got tall trees next to relatively shorter trees, and wind moving across here is going to spin through the system and become very convective with lots of turbulence. And we can also measure coefficients of coupling. And in this case, we've got decoupling coefficients, which are going to be essentially the inverse of coupling, where relatively smooth systems like alfalfa or a crop patch that's relatively flat are essentially going to be entirely decoupled with very little exchange between the atmosphere and the ecosystem. And then you've got other systems that we think of as having a high coupling coefficient or very low decoupling coefficient, where there's a very efficient transfer of energy. So here also note a completely smooth surface has a decoupling coefficient of 1.0. And canopy in which the air is identical to that in the atmosphere has a decoupling coefficient of 0. So if it's relatively well mixed and there's no differences, then that decoupling coefficient is 0. So these are things that we actually measure and they get put into models and they help us understand the amount of energy and water vapor that's transferred out of ecosystems. So last thing you'll see, the authors are talking about boundaries versus centers of ecosystems, and the boundaries are places where you often have a lot of mechanical turbulence. It's important to read through that. And lastly, I'm going to talk a little bit about snow and its importance in ecosystems. And we talked a little bit about how snow has a high albedo. And if we take a look at, for example, a north-facing slope in the northern hemisphere, that snow is going to melt out a lot later. You can see this has a high albedo. And that's going to be a lot different energetics here, where shortwave radiation coming down is going to get absorbed instead of being reflected. But another thing about snow is that it gives us seasonality and changes the energetics of the system. So often in a deciduous forest, for example, there's a period of time when there are no leaves. And during the spring, those leaves come out. And once those leaves come out, the energetics of a system changes a lot. So leaf out alters the energy exchange by changing albedo. So before you had leaves, you tended to have more albedo, and especially if you have trees with snow on the ground, if there's no leaves on there, you're going to have a lot of albedo. And once those leaves come out, a lot more of that energy gets absorbed. Even if there's no snow on the ground, you're still often going to have a lot higher albedo of a system. So leaf out changes the albedo of a system, but it also increases evapotranspiration at the expense of sensible heat flux. So if you have a forest, for example, that's bare, shortwave radiation coming down is going to get absorbed. But because there's a lot less surface area to transpire water, most of that goes into heating the surface and then sensible heat flux. But once those leaves come out and we have a lot more transpiring surface, that energy that's absorbed by the leaves goes into sensible heat flux. And I'll show you one figure. And this is data from Hubbard Brook. Again, that's in the northeast of the US. And in this paper, what the authors did is take a look at a couple of things. The first is snow depth. And I think, if I remember correctly, this is data from a particular year, April, May, and June. And this is the snow depth. So in March, you've got somewhere on the order of 30 centimeters of snow. Some of it melted. There's another snowfall event. And then by mid-April, the snow is gone. And once the snow is gone, look at the soil temperatures here. 0 to 4 up to 14 degrees Celsius for temperatures. That the soil itself stays relatively cold. It's relatively insulated. But once that snow disappears, the temperatures start to climb. And it gets warmer and warmer and warmer. And you can see, after a certain period, it flattens out. It's still sunny, but the energy, instead of going into heating the soil, we have bud burst right here. And once you have bud burst, meaning leaves are produced, a lot more energy goes into sensible heat flux. And instead of heating the soil, for example, a lot of that energy goes into evapotranspiration of water. So when you have very few leaves in a system and the snow is melted, you go from a high albedo system to a lower albedo system, but one where most of that energy is partitioned into warming of the ground in the ecosystem. And then that generates sensible heat flux. But once the leaves come out, the energetics shifts from one where it's sensible heat flux and ground heat flux to one where most of that energy goes into evaporating water. So there's a big seasonal patterns, and especially in these deciduous systems, in partitioning of, well, first differences in absorption and reflection of energy, and then differences in whether it's absorbed and you get ground heat flux or sensible heat flux, and then once the leaves come out, changes to a system that's really dominated by latent heat flux.